Do you see it?
Yeah.
Okay. Okay. So, thank you. Yeah. 1 second. I put pointer. Okay.
Yeah.
Thank you for the introduction, Shugo. And it's a pleasure to be here and to have the possibility to present the work and also in this nice event. So yeah, my name is Francesco Calavella. I'm now a postdoctoral researcher in Kyoto University, but today I will show you something, one of the latest work that I carried out during my PhD under the supervision of Luis Suezo and Felix Casanova in San Sebastian, Spain. The title of the talk is Gate-tunable and chirality-dependent charge-to-spin conversion in tellurium nanowires. We will see that also in this case, we will tackle a little bit the relationship between the symmetries of material and in particular the symmetry breakings in materials and the relationship with the charge-to-spin interconversion phenomena, how this affects the transport of spin or the generation of spin in these peculiar materials. And we were studying this because in my previous group, we were really interested on spintronics and spin orbitronics, which, as you all know, is this branch of material science that aim to use the spin degree of freedom of electrons to store and manipulate information, with the objective of at least partially solve the power consumption problem that we will face and we are facing with traditional electronics. So there are already famous examples which use charge to spin and spin to charge conversion to write and read the memory bit in devices. Here there is the spin orbit torque device as a already quite famous example. And on the other hand, we have a mesologic device in which on one hand we have the use of spinel effect to convert this a charge current into a spin current, which can transfer spin angular momentum to the ferromagnetic bit element of information, while on the other hand, through inverse spinel effect, we can read the magnetic state of a ferromagnetic element. Now, this concept has relied typically on this spinel effect in heavy metals, and heavy metals which typically have high symmetric structures. This means also that we have symmetry constraints for the configuration of spin current, charge current, and spin polarization, which in this case has to be mutually perpendicular. So, nevertheless, we also know that in recent study, it has been demonstrated that the symmetric configuration of the material at the microscopical level can reduce the symmetry constraints, allowing for new spin-to-charge conversion configuration, which may be very helpful for the design of new spintonic devices with different configuration and geometries. So for this reason, and also because this relationship between symmetry properties and spin to charge conversion phenomena is very interesting, we decided to explore a symmetrical property of matter, which is the ultimate expression of broken symmetries, so like chirality. As you all know, chirality, we can encounter it a lot in nature. One example is our human hands, which cannot be superimposed to one another by rotation and translation alone. This means that chiral figures basically automatically breaks all mirror and inversion symmetries. We will see that this is very important for the phenomena that we will explore. So to study this, we decided to take the simplest material that we could think of that has a chiral structure. And in this case, we used trigonal tellurium. Tellurium has naturally is a narrow bandgap semiconductor, which is formed by one-dimensional helical chains, which winds up around this chiral axis, clockwise or anti-clockwise, and that they are kept together by van der Waals forces. So we managed to synthesize single crystal nanowires, of which you can see the cross-sectional TM image here, which we could use and deposit on substrate to be contacted then with standard E-beam lithography technique. In these samples, we could explore we could perform magnetotransport experiment with which to evaluate the magnetoelectrical properties. So first, we took a measurement that I would call here current independent, meaning that we were averaging between contribution of resistance obtained with positive and negative current. And we can see that we have a resistance versus temperature behavior, which is monotonically decreasing with the temperature, meaning that even if we have a semiconductor, here we are in a degenerate condition. And this is well known because tellurium gets self-doped by the presence of atomic vacancies in the crystal. So we are basically with the Fermi energy inside of the valence band of the material. Moreover, we observed also that we have a peculiar magnetoresistance, which changes a lot when the magnetic field is applied perpendicularly or parallel to the chiral axis. We have a positive magnetoresistance in one case and the negative one in the other. So this is already quite interesting, but what we were interested to are, as I said before, the current-dependent measurement with which we could see how the effect of momentum of electron can translate in a spin polarization. And to understand this better, we can have a look to the spin texture of tellurium, which, as you can see here, is formed by these branches, which are actually spin-splitted. This is an ab initio calculation given us to our collaboration, in which we can see this narrow band gap here and this spin-splitted configuration induced by the high spin orbit coupling and the inversion symmetry breaking. If we take a zoom here with an effective Hamiltonian model developed also by our collaborators in Germany, we can see how we have these two spin-splitted band, and we can also see that they have opposite spin polarization with spin momentum locking. And interestingly, if we take a cut of this at this energy here, we can see that this spin momentum locking configuration gives us a spin texture which is quite unusual, and is a radial spin texture, unlikely in Rashba system where we may have a helical spin texture which goes tangential with the Fermi circle. Moreover, what we can see is also that if we change the handedness of the wires, we have the reversal of the sign of this spin texture, which points inward or outwards depending on the handedness of the crystal. Now, if we take this in mind, our idea was to use Edelstein effect-like mechanism to detect a current-induced spin polarization, basically. And so if we apply a current to our material, what happens is that this Fermi circle would be shifted in the K space, and this will give us a homogeneous spin density, which can then interact with the external magnetic field. Now, taking angular dependence measurement of the resistance at a given applied current, we can see actually how the resistance behaves. And here we have a very interesting signal, because we can see both the maximum and minima relative to positive and negative magnetoresistance at field perpendicular or parallel to current, but also that when the field is parallel to the current, we have two different levels of resistance when the field is parallel or anti-parallel to the current applied. And as I said, this can be seen as an interaction between the external field and the spin density generated by the current. So having an effective field that is lowered or increased by the current applied. If we reverse now the current direction, what we have is the generation of the opposite spin density, and so an opposite behavior of this this angular dependence. And this is basically a unidirectional magnetoresistance effect, which can be also seen as a rectification effect or a non-reciprocal charge transport. And this is basically the manifestation of this charge to spin conversion phenomenon. Now, what is also interesting is that measuring different wires and matching them with a TM picture, which could give us a one-to-one matching of measurement and handedness of the crystal, we saw that these characteristics were getting reversed when the handedness was reversed, accordingly to the mechanism that I showed before. So if we have a look to have a more visual representation of this signal, so we take the half difference of resistance obtained with positive and negative current, we obtain basically the equivalent of a second harmonic measurement. And here we can see how this sine-like curve, which has a funny shape because of the non-trivial configuration of the spin texture in the 3D space of tellurium, we have nonetheless a reversal of this sine-like shape and also a linear behavior with the current applied. So this amplitude goes linearly, this amplitude of the signal goes linearly with the current applied, which is again supporting what we suggested as a mechanism, a microscopical mechanism, which is an Edelstein-like measurement mechanism in which the more current we apply, the more we shift the Fermi circle, and the more we generate a spin density. Now, I see that I'm short in time, so I can also tell you that we observed a linear behavior with magnetic field, which is a little bit more difficult to explain in this toy model that I showed you before, but that it has been observed also in other material, and that is consistent with electrical magnetochiral anisotropy, which had been observed in other chiral system, with the resistance having a dependence here in this phenomenological formula, which goes not only with the quadratic, with the square of the magnetic field, but also with the mutual orientation of linearly and mutual orientation of magnetic field and current, and with the chirality of the material. We also were able to control this amplitude through an electrostatic gating, which basically was acting on the Fermi energy position in the material, basically changing the efficiency of this Edelstein-like effect mechanism. And we could also, at least qualitatively, compare this with our theoretical model, in which we can see that the spin generation has this trend with respect to the Fermi energy position in the material. So with this, I would like to conclude. I hope that I convinced you that the symmetries of materials are very important for spin-to-charge conversion mechanism, that electrical magnetochiral anisotropy can be explained at the microscopic level with an Edelstein effect acting on the radial spin texture of the tellurium, which we have induced spin density collinear to the current direction, which is highly unusual with respect to other material. And it reverses for opposite crystal handedness, which we can control also this with electrically, with a standard gating technique. And finally, the carrier materials may allow novel designs for spintronic devices. With this, I would like to thank all the people of my previous group, Masashi Shiraishi, which allowed me to be in his group and continue my research, and all of you for your kind attention.
Thank you for an exciting talk. Let's move on to the question session. So does anyone have a question? Almost 1 or 2 minutes remained for the questions. Okay. If there's no, so let me ask you questions. So please go to the slide 10.
Maybe. Yes. Yes.
10.
Yes,
please.
yes.
Okay. I have a question about the shape of the angular dependence. So is there sample dependence of this angular dependence?
Yes. Yes, this is actually a question that I almost always receive, but I don't have the time to go in this detail. Basically, here we have, unlikely in Rashba system where we have a perfect sign typically, because we have basically a circle. Here we have a 3D egg, which doesn't have efficiency in all directions, but in principle we have the possibility of convert spin to charge in all directions in tellurium, because all the symmetries are broken. So somehow, because I think because in homogeneity of current direction, and also because the sample is not completely ideal, we have these spikes, which are obviously more prominent at this when the field is parallel to the current, because we have like the maximum efficiency somehow. And this, yes, indeed changes from sample to sample, and we think that it depends on the Fermi energy position, because we notice that depending on the thickness of the nanowire, we have more or less self-dopant. So the starting point is always different. And if you look at the gating here, you see that in this sample, we had almost a flat curve and only these spikes here. But then when we increase the voltage, we start to see the shoulder of the. So yeah, we start to notice this, and we noticed that with the gate we could pass from one thing and the other, and we didn't really go deeper into the really mapping of the shape because it's very, very difficult. And then the geometry, the real geometry of the sample doesn't allow you to really conclude something quantitatively. You can say something qualitatively, but not qualitatively.
I see. Yeah. Thank you so much.